Welcome to the second objective, learning target for our lesson on how second derivatives shape a graph. We're going to be able to apply the second derivative test to find relative extrema. That is correct. The second derivative test does the same thing that the first derivative test does, and that tells us where we have relative mins or maxes. And remember, a relative min or max has to occur at a critical value, where the first derivative is equal to 0 or undefined. So there's step number one. And then it involves finding the concavity around that particular point in order to be able to tell, does it, for example, cave downwards or cave upwards around that point to make a relative minimum or a maximum. So if you take a look at this person that's doing yoga while they're, I'm thinking that they're on Khan Academy right here probably. So you can see that her body makes something that is concave down, right? And if we take a look at maybe at her belly button right there, which would be a critical value, and the body concaves down. It caves away from that tangent line there, and that indicates that we have a relative maximum at that point, and that is the basis for the second derivative test. So we're going to start by looking at this very simple example. Note that for f of x equaling, we got a cubic polynomial, has a relative maximum at x is equal to 1. Yeah, we can see we have a relative maximum at 1. We have a relative minimum at, looks like at 3. It's asking us what is the value of the second derivative at x equals 1. So here, let's find the second derivative. It shouldn't be too terribly hard because we do have a polynomial here. So f prime of x is equal to the 1/3 and the 3, when it leapfrogs down, it's going to cancel out. Just give me x squared minus 4x and then plus 3. Second derivative, I have 2x minus 4. And I want to find the value of x equals 1 there. X equals 1 is a critical number. So it's a critical number where a possible relative minimum or maximum happens. We saw from the graph it's definitely relative maximum. If I were to stick in 1, I would get 2 times 1 minus 4 is 2 minus 4, which is negative 2. Since the value of the second derivative is negative 2, that means that it is concave down here. So think of a graph. For example, we draw ourselves some sort of graph. It's concave down with a tangent line, and that tangent line here has a horizontal slope. It's a critical value, so the slope of it is equal to 0, and we're caving away from it. Right? We're bending away from it. The tangent line is up above it. This must be a relative maximum, and that's exactly what happens on the graph as we saw right there. All right, so here is the second derivative plotted out, and here is the value of the second derivative. It's negative 2. So this is basically what I do for the second derivative test. I find where our critical numbers are, and instead of making little intervals, we plug that critical number into the second derivative and just check to see if it's positive or negative. If it's negative, it must be concave down around that shape, indicating that we're bending downwards from that tangent line, that horizontal tangent line, making a relative maximum. Let's see the same thing happen over here at the relative minimum at 3. So we already found the second derivative, piece of cake, and we want to plug in, this time, 3. So f double prime of 3, 2 times 3 minus 4, 6 minus 4, this time is equal to 2. So this time we have a shape that's concave up because the second derivative is positive around our horizontal tangent line. Let's put on our horizontal tangent line. If it caves away from, upwards from that tangent line, this time it must be a relative minimum. And let's see that on the graph for that one. So again, here is the value of the second derivative. It's positive 2. It's concave up here, concave up, and it's going to give me a relative minimum. Okay, so let's then formally state the second derivative test. So understand, first of all, second derivative test does not test for concavity. The second derivative test tests for the exact same thing that the first derivative test tests for, which is relative mins or maxes. And our starting place is where is your derivative, first derivative, equal to 0 undefined? What are your critical values? We need critical values, okay? So let f be a function such that f prime of c is equal to 0, and the second derivative of f exists on an open interval containing c. It needs to exist because we're going to plug that value of c into the second derivative to see if it's positive or negative. Right? Right. So here's the first part of it. If f double prime of c is greater than 0, then f has a relative minimum at c comma f of c. Okay, so this is the way that I want to think of it. I first need to have a critical value. So the first derivative is equal to 0 at c, and the second derivative is greater than 0. It's a positive number, so it's concave upwards. It's going to cave upwards away from the tangent line, and that's going to be a relative minimum. Second part of this thing. Again, we have a critical value. We have a critical value. We plug the value of c into the second derivative. This time we have a negative number. So the second derivative at c, our critical number, is less than 0. It's concave downwards. We're caving downwards away from our horizontal tangent line. This is going to give us a relative maximum at c comma f of c. Okay, so the first derivative test tests for relative mins and maxes based on increasing and decreasing. The second derivative test also tests for relative mins and maxes, but this time it's based on concavity. It's the value of the second derivative, but we still have to find the first derivative to find its critical numbers to plug into the second derivative. Now notice that it only says where the first derivative is equal to 0, but it doesn't say undefined. So think about that for a second. Why is that left out? That part is going to be left out because where it's undefined, you're not going to be able to stick that into the second derivative because you can't take the derivative there.